All right. Welcome back. So we continue mostly conceptual today with maybe one problem at the end, one or two problems at the end. So last time we defined what a force is. A force is a push or a pull from an agent at a point of contact. The exception being gravity, of course. Gravity is the only force we will see in this class where contact is not required. Everything else requires there to be contact between the two objects for a force to be exerted. If I push on my phone across the table, that is a result of the fact that I am pushing on it. When I stop touching the phone, there is no longer a force that is acting on the phone from my hand. The agent of me has vanished. It has other things it's in contact with, like the table itself, and so the table, as a result, exerts a force on the phone. So other things we saw, forces can come from animate and inanimate objects. I can push on the phone. I could tie a rope around the phone and pull on the phone. There, the point of contact is between the rope and the phone. So the force from the rope is acting on the phone, we would say. While I am touching the rope, I am acting on the rope. The rope is acting on the phone. If I'm tossing a ball into the air, I am exerting a force on the ball as I lift my hand up. But as soon as the ball leaves contact with my hand, the force from my hand goes away, and in the case of a ball thrown into the air, the only force it feels is the long-range force due to gravity, which does not require contact. Similarly, when the ball falls back into my hand, it's falling downward via gravity, but then when it hits my hand, there's additionally a new force acting on the ball, the force from my hand on the ball. And we saw, for example, evidence for what I am defining to be, or calling Newton's first law, sometimes called the law of inertia. The book version defines it as something like, so let's see, I could call this book. It says something that if there is no net force, and the use of net will become clear in a minute. Acts on a body, the body moves at a constant velocity. Which could be zero. The velocity could be zero. It could also mean that the object is moving at a constant speed in a given direction, i.e. moving in a straight line. We saw that with the air track. When I was not touching the disc after I gave it a push, it traveled in a straight line at a constant speed. Alternative ways of saying this might be, I might say that net forces, or just forces for right now, causes changes in motion. I.e. changes in velocity. You could think of this in a sense as a way of defining force. Forces are what change velocity or cause accelerations. And then we saw that Newton's second law states a quantitative way of relating force and acceleration. It says that the force acting on an object equals the mass of the object times the resulting acceleration. And sometimes this is written like this, which I think makes it a little bit more clear of the cause and effect. Right, so here I would say the force is, the cause, and here the acceleration is the effect. From the cause, with mass being the proportionality relationship between the two. It also shows that if you want a given acceleration, you need to exert a force. But if the object has a very large mass, in order to get a given acceleration, you have to also increase the force. If the mass is big, the denominator is huge. In order to make the acceleration some number, the numerator also has to increase as well. And we called this m the inertial mass of an object. I will likely start dropping the word inertial. We will just say that this is the definition of mass. Excuse me. Now, Newton's second law, another way that it's usually written is it says that the net force acting on an object results in an acceleration given by A equals, I could write F net divided by M. So now what does this mean? This means that you can have multiple things acting on an object, and all you have to do is just properly add up the forces. So think of a game of, there's a big box on the ground and there's a rope attached to the box. You yourself could go and pull on the box, through the rope, and that might cause the box to accelerate. And if the box is really heavy, like it's filled with bowling balls, it will accelerate much slower by you pulling on it than as if the box was empty. You can achieve accelerations quicker. Larger accelerations, or get larger velocities quicker, rather. If, for example, you and your friend both pulled on the box, you got two ropes, and you each pulled on the box in the same direction. You both are then working together to pull the box and accelerate it in a particular direction. There, in this case, the forces you are exerting on the box are combining in a way that allows you to achieve a larger acceleration for a given amount, for an increased amount of total or net force. Now, why net and not sum? Net because the forces can also work against each other. Think of a game of tug-of-war. You have one long rope, you have people on each side, and they are each pulling in different directions. And if they are both pulling by the same amount, the rope doesn't move. In that particular case, I would say it's because there is no net acceleration, so therefore the velocity cannot change. And if the velocity was 0 to begin with, it will then stay at 0, and the rope does not budge. So by the net force, the way I would define it in 1D, the net force, which I'm not a huge fan of. I like writing it as just full out the sum of forces. Tell me all the forces that are acting on the object. I will add them all up, and that is therefore the net force. Let's improve this definition by recognizing, given the language we're using, and our intuition says, like tug-of-war, if I'm pulling in different directions, then the forces seem to cancel each other out. Where if I'm pulling in the same direction, two people pulling a box, for example, the forces seem to work together. That sounds like a vector, in that the direction the force acts on an object has a directionality. And if they point opposite each other, they will cancel out, versus if they're pointing together. So force is also a vector. And that might not be too surprising given Newton's second law, because acceleration equals force divided by mass. And mass is just a constant quantity. So that is not a vector. And acceleration is a vector, which means force must be a vector. So I might actually, a more appropriate way of writing Newton's second law might be something like this. The acceleration vector is a result of the force vector divided by a constant scalar, the mass. And so how do we upgrade this and combine these two ideas? I can write, I think the best version of Newton's second law, in that it's saying the net force equals the acceleration on the object. So I'll write this as the sum of force vectors equals the mass times the acceleration on the object. That is definitely worth a highlight. So again, you're saying if there's pushes and pulls, maybe there's many of them, maybe there's thousands of them, maybe there's only one. If I add them all up as vectors, that then equals the mass of the object times its resulting acceleration. An object can only experience one acceleration, really. If there are a bunch of forces acting on it, I can't say that, if a bunch of people are pushing on a ball, ultimately the ball moves in one particular direction. The ball cannot move in multiple directions simultaneously. There is some net overall acceleration that results and can be measured from the net sum of all the forces. E.g., suppose, let me stick with 1D, I guess, for right now. So 1D, here's my origin. I'm going to say positive is going to the right. I have some box. And I'm pulling on the box with some force. Maybe it's attached to a rope. And we'll learn about how to identify what forces are acting on it. But for now, let's just take that I'm pulling on the box. There is some force acting on the box that has some mass m. What I could say then is that the resulting acceleration equals the force from the rope divided by the mass of the box. And if the force is a pull to the right, then this I would define as a positive number. As a result, A is then a positive number as well, since mass is intrinsically positive. Negative mass has no meaning. So then as a result, I'm pulling the box to the right. It therefore will begin to accelerate to the right. In the game of tug-of-war, where you have a box of mass m, and you have two people pulling on the box in opposite directions, you might think intuitively that seems like the box should stay still. And if the box originally was staying still, it would. If this entire thing were taking place on an ice rink where everyone was already moving at some velocity, the equal pulls would just cause everyone to keep moving in a constant at a constant velocity. So here I would say force 1 might be plus F, that's the tug to the right. And then force 2 might be negative F, that's the tug to the left that's occurring. Then I could say Newton's law then says the sum of the forces equals the mass times the box's acceleration. The sum of the forces is the force 1 plus the force 2 equals the mass times the acceleration. Force 1 was plus F, force 2 is negative F equals the mass of the box times its acceleration. The left-hand side, of course, then just becomes 0 equals the mass times the acceleration, or the resulting acceleration is 0, or the 0 vector. It is not accelerating at all in that case. If it was moving at constant velocity, it stays. If it was originally at rest, it stays at rest. Now with vectors, we spent a lot of time thinking about how we can understand multiple dimensions using vectors. For projectiles, we usually were dealing with 1- and 2-dimensional motion. We could have done 3 dimensions. We could have done 8 dimensions. Vectors, you just keep adding on components that make sense for what you're doing. And we had the benefit of being able to treat each dimension independently of one another. Again, that experiment just seems to hold that that's true, that each dimension behaves roughly independently of one another. I was talking with another physics faculty member, Professor Ray. He would not say that, actually. But I think we're saying the same thing, just using different words. So his counterpoint, which I understand what he's going for, though I would still say what I say is fine. He would say, well, what about if there's air resistance? If there's air resistance, that occurs both in the x and the y direction if a particle is moving. And that affects the motion in both. So you might think that the x and the y directions they are interacting in a way with each other. And I get what he's saying. He's saying that you have a force, in that case, the air resistance force, that is kind of acting at an angle compared to the object's motion, so that there is an x and a y component. But you can still solve the problem by breaking, say, that air resistance force into an x component and a y component, and then doing each dimension independently of one another. That is what is meant by each dimension being independent. I can treat everything that's going on in the x direction alone, and then I have a different equation for what's going on in y. And sometimes there are things that are related between the two, but nonetheless, you can always do all the x's over here, all the y's over here. Anyway. But this gives rise to the idea of superposition of forces. Which all that's saying is that the net force is the sum of all the forces. We just saw that. You can add up all the forces, and if they're vectors, you can take into account the fact that there might be dimensionality to it. There might be x components and y components of the vector, and that's fine. You can get a net single vector that has a single x component, a single y component. That is the sum of all the x components and the sum of all the y components. And that can be treated just as a nice simple sum. That is the idea behind superposition. You can just add everything up and treat each individual element as just another term that you just add on, and you get the right answer. We can also, again, through experiment, pull back in the knowledge that each dimension is independent. Or I'll say each dimension can be treated separately. Here's my simple example. Suppose this is a bird's eye view. I'm looking down. Here's the x and the y direction. They're positive towards the right and up. And suppose I say that there's a force that is acting on the box, but it is angled at a 45-degree angle. So this angle here is some 45 degrees, say. I could ask then, what is the resulting acceleration on the box? So you might think F equals ma. Now it's incorrect. But we're dealing with vectors, so it might be the case that I want to know how fast is it accelerating in the x direction, how fast is it accelerating in the y direction. For projectiles, remember, we always had it so gravity was only vertical, so the horizontal didn't care. Now in this case, the force is pointing both horizontally and vertically, so we have to take that fact into account. So I always start as super general as possible. I always know this must be true. The sum of the forces acting on the box is equal to the mass of the box times the acceleration of the box. And if I wanted to write this as a vector expression, I'll use the column notation. I'm going to need more space. I could ask, okay, what part of this force, there's only one force, so that's nice. So I can just write one term on the left. What is the force? The force is pointing at a 45-degree angle. So I can write it down. There's both an x component and a y component. Let me redraw it here. Here's the magnitude of the force. There's some angle that is 45 degrees. I again can ask, what is the x part and what is the y part? And that looks no different than what we've seen before. So again, this would be x. The x component would have a cosine factor, and the y component would have a sine factor. Then that must equal the mass times the acceleration in the x direction, acceleration in the y direction, the acceleration vector. So if I wanted to, again, like we did with projectiles, I could look at the top line, and that's what's telling me what's happening in the x direction. Then I could look at the bottom line, and that's telling me what's happening in the y direction. So in the x direction, I would say f cosine of theta equals max. And I could solve for the acceleration in the x direction. That would give me a number. And then similarly, I could do it for y. Get the acceleration in the y direction. That would give me a number. And then I would know in 2 dimensions how the object is moving. Since the angle is 45 degrees in this case, actually it will turn out that the acceleration is the same in the x and the y direction, because cosine and sine of 45 degrees are the same thing. All right, so let us see here. Yes. But now we have to ask ourselves, how do we properly identify forces? We're going to do so using force diagrams. A challenge with this part of the course, particularly if you saw physics in high school, is that, again, I apologize to your physics high school teachers, is that I feel like a lot of them teach physics in high school as there are certain problems and here's how you solve those particular problems. If you ever see an incline, this is what you do. If you ever see a spring, this is what you do. And that sort of thinking is incredibly dangerous for a college-level physics course, because I could dream up any problem that involves springs that could be solved in an infinite different number of ways. Similarly, I could think of inclined planes that require forces or energies or momentums. All of those things I could think of, just because there's an incline involved does not mean there's a given way to solve the problem. So relying on problem-solving algorithms can be dangerous if the algorithms are crap, essentially. I'm just going to say it. What is better is to memorize, if you're going to memorize anything, memorize a problem-solving strategy that will work regardless of what the problem is. So any sort of rules or instructions or guides that I give you, I intend for them to be as general and widely applicable as possible. I rarely will ever tell you how to solve a particular problem. I'm trying to teach you how to solve a wide variety of problems. Because again, teaching to a particular kind of problem is dangerous because I can always dream up other ways to ask the problem that involve different techniques. And I think that happens a lot. Like, if you saw physics in high school, you might have known about this thing called the normal force. But students 90% of the time constantly misuse it because they always say, okay, normal force equals mg, and that's always true. And that's not always true. A lot of the problems you see in high school happen to be the case where that was true, but the normal force is not always that case. So if you memorize that, that's a really risky thing to memorize. Memorize instead a strategy around how to tackle any sort of problem. And then this strategy can be applied to any problem that is thrown at you. So let's learn how to draw force diagrams. First, I have to define a couple of terms. So I have to define what I call a system and what I call the environment. The system is something we will see time and time again in this course, and we're going to build its complexity as we go. Just kind of how, like with coordinate systems, we're building our ideas, kind of what a coordinate system means. Here we have a system, which the system I'm going to define as the object or objects you want to study and analyze, i.e., figure out the motion of. Contrast that with a term I'm going to call the environment, which in simplest terms is just everything else. Outside the system. So the system is the thing you want to study the motion for. If I'm rolling a ball down a ramp, the system in that case, I'm analyzing the ball. That's the thing I'm analyzing the motion of. If I have the Earth and the Moon orbiting each other and I want to study their motions, I might define my system as the Earth-Moon, for example. Or if I'm just looking at the Moon or just looking at the Earth, I might define just the Earth or just the Moon as the system. And to use that example, if I define the Earth as the system, then the Moon is part of the environment. If I define the Moon as the system, then the Earth is part of the environment. If I define the Earth and the Moon as my system, and I want to understand their total motion, then the system might include things like, like the sun, something that, the other planets, other stars. They lie outside of the system and are part of the environment. And what we're going for here is that given you define your system, the environment is where all the forces come from. Define a system. All forces acting on the system come from the environment. you do not consider things inside the system as being able to exert forces on the system. All that's saying is you can't self-impose a force on yourself if you are the system, for example. The Earth cannot impose a force on itself when you're analyzing the motion of the entire Earth. When you're analyzing the moon and the Earth together as the system, you ignore their tugs and pulls between each other. You're only thinking about how they, as a group, are moving around, say, space from the sun or the other planets or something. That, if you've seen some of this stuff before, that ties into the idea of Newton's third law, and that those interactions will not matter at all. So we are not including internal forces. We're only thinking about external forces here. External forces being things coming from the environment. So let me work through the steps here with an example. Suppose I have a box that is in space, and attached to the box is a rocket that is trying to push the box to one side. And I am trying to study the motion of the box. So box in space. Rocket pushing on box. Here it might be simple enough for you to think, okay, yeah, there's a force from the rocket pushing on the box. But let's actually go meticulously through the steps so you can see how you might apply these steps to more complicated problems. First step is to identify the system in the environment. And in doing that, I will define the system by drawing a box around the system that is ever so close to the edges of the system. So let me use blue. So if my system is the box, I'm going to draw a blue dotted box around. And I'm going to call that the system. The system is everything inside that box I just drew. So I'd say step 2 is box in system with a closed curve. Closed just meaning I don't just draw a line. You know, it is enclosing something. Then, given your picture, you can easily identify all the contact forces on your system by asking what in the picture is touching your blue box. Blue box. So I might say all objects touching the system. Or I might even say the system box that you drew. Exert a contact force. And let's identify that. So actually let me just copy and paste. Copy, paste. So here I could stare at my system and say, what is touching that blue dotted box I just traced out? And you might say, well, it seems like there's something here that is touching your system. Again, you don't care about the box itself because that is part of your system. You're looking for anything from the environment that is touching your dashed little blue box as I drew it. So then this looks like it's the rocket is touching the box. So in that case, I would say that the rocket has a contact force with your system, in this case, the box. So I would say the next thing is to give the contact forces symbols and names. So I might go back here and I might say that this is the force. I'm going to say the force from the rocket. Notice I have not yet said anything about directions or how the magnitude of the force. Right now, all we're doing is just identifying what the forces are. Then we can worry about giving them numbers, giving them directions, drawing arrows, all that sort of thing. And then the last step is to identify long-range forces. Long range forces, if any. So gravity, for this class, it will be gravity, where you then have to ask, is there gravity in the system? If so, let's give that a symbol as well, force due to gravity. Here, we took the example of a box in space, so we're going to assume we're far from any stars or Earth or the moon or the sun, so that any gravitational forces being exerted on the box is very low. So we're not going to consider a gravitational force right now. This procedure has helped us now identify all the forces acting on the system. The F equals ma. The m is the m of the system. The acceleration is the acceleration of the system. The sum of the forces is the forces acting on the system. Right, this sum of the forces is forces from the environment acting on system. This mass is the total mass of the system. We're doing this as the box, so it would just be the mass of the box. But you can imagine, what if I were to open up the box and it was revealed that inside the box was, billions of jelly beans? Then the total mass of the system would just be, since all those jelly beans are inside the system, the total mass of the system is just the mass of all the jelly beans. And then this acceleration is the acceleration of the system, which is a result of these forces. With this in mind, or if this is successful, how much room do I have left on this page? Okay. Once you've identified all the forces, you can then draw a free body diagram. Where's my mouse? Sometimes abbreviated FBD. Free body diagrams represent the system as a dot. and draw all contact forces as arrows emerging from that dot. Pointing in the direction the force is acting. So the idea behind a free body diagram is you take your nice pretty picture drawing and you make it a more simplified image where you just have a dot in the center and that represents your system. And then you draw arrows that represent all the contact forces and maybe the occasional long-range force that is acting on the system, and those arrows are pointing from the dot in the direction they're acting. So in the case of the box, I would say the system is the box, so I'm going to write that as just this dot, so maybe that's box. And then we identified one force, the force of the rocket. And here you have to use more knowledge about the problem and what's going on. The rocket, if its exhaust is going to the left, it's just going to be pushing the box to the right. So I would draw this as a dot with an arrow, and I would say this is the force of rocket. This is an example of a free body diagram of the kind of force diagram picture that is drawn up above, of the actual picture of the box with a rocket. The free body diagram, it's a much simplified version, and it cuts out all the noise, so you can then think about vectors and directions, and gives you an easier way to tackle the problem. Now notice I had the drawing, all the arrows are emerging from the dot. You might think, well, the force is pushing on the box, so shouldn't the arrow be pointing to the dot? No, that is not the convention. The convention is that you're drawing all the vectors as they're acting on the system, the dot. And to create the net vector, that is represented by the sum of all those vectors, that emerge from the dot. So the idea is that the free body diagram is trying to capture directionality of the forces. Arrows pointing to the dot, away from the dot, that is not the point of the free body diagram. They all start at the dot, emerging from the dot in the direction the force is acting on the system. How am I in time? Okay. Let me do a few examples. And you will do these as well when we meet in person. So let's again do the box rocket. But let's assume this is also happening, close to the Earth. And the question now is, what is the force diagram for my box, which I'm telling you the system is the box. And what is the free body diagram for this box as well? So we could go back to our previous list and remind ourselves. You identify the system. Okay, the system is the box in the environment. So then I could go back here. I could identify my system. I'm going to draw that as that. Okay. Box and system with closed curve, done. All objects touching the system box exert a contact force. Give them names, symbols, and then identify long-range forces. All right, so I could go back to this, look at what is in contact with the box, and I see the rocket here is touching my blue dash box that I've drawn. So there's a contact force there. I'm going to call it the force from the rocket. And then there's nothing else touching my system. So in terms of contact forces, I'm done. Then I have to ask, last step, identify any long-range forces if applicable. In this class, that will only be gravity if gravity is around. We are near the Earth, so I would also say there's a force due to gravity, which I'll just put off to the side here. And I might even say long-range force, just to identify that there's also that guy that we have to consider. Then the free body diagram. I represent my box as a dot. Then I ask, what are the forces acting on this box that I've identified? I've identified two now. Can I give them arrows? So the rocket is pushing the thing to the right, so I would say that's force of the rocket. And then gravity is pulling the object towards the ground, so the way I've drawn it, I might draw this and say force of gravity. So that would be my free body diagram. There are two forces acting on it, and they appear to be perpendicular to one another, at least based on this drawing. How about here's the ground. On the ground sits a chair. And in the chair I sit upright near the edge, with my feet firmly planted on the ground. Oops. And I am given in the problem that the system is you sitting. So again, I would draw. It doesn't necessarily have to be a box, but it has to be something that encloses the system of interest. So there is my system, me. Now I zoom in and I think about, okay, I try to identify what is touching the system. That must then exert a contact force. So it looks like my bum is touching the chair right there. So I might call that force from chair. That is acting on my posterior. Then my feet are touching the ground, so this might be force from the ground. That is acting on me as well, because my feet are part of the system. Then it does not look like there's anything else outside the system touching me. So then I would also ask, what about gravity? Indeed, assuming we're doing this on the Earth, right, there's also gravity. So in that case, my free body diagram, here I am as a dot. Gravity is pulling downward, so I could write that as F grav. The ground is touching my feet, and it's not pulling my feet into the ground, it's resisting my feet from sinking into the ground. So that would be a force that is pointing upward. So I would say that is F ground. But then I also have the chair acting on me, and the chair, again, I'm not sinking into the chair. So the chair must be resisting the fact I'm trying to sink towards the ground. So the chair also would act on me, pointing upward. So notice here, when there are multiple forces pointing in the same direction, I could think of it like a vector sum, right? The sum of the vectors pointing up is just, base to tip, base to tip. So that would be my free body diagram for me, the system, sitting in a chair with my feet on the ground. There are 3 forces I would have to consider if I wanted to do F equals ma. All right, so we will also do a bunch of these as well when we meet in person. Let's talk a little bit more about this gravitational force. And particularly, I'm going to talk about the gravitational force near the surface of the Earth. If you're not near the surface of the Earth, the equation we're about to get is junk. So we've already studied acceleration with regards to gravity. We've talked about free fall motion, where if you're near the surface of the Earth and there's nothing else acting on the object, remember that was a key assumption I said, but did not really explain why before, that as long as nothing else is acting on the object, it will accelerate downward at 9.8 meters per second squared. And that can be experimentally verified. We can now use that to say something about the force that gravity is pulling on this ball in order to cause it to fall at 9.8 meters per second squared, for example. So again, let's take the case of here's the ball, and I'm near the Earth. I always like to draw the Earth just to make it clear that I don't forget about gravity. But the ball is not touching the Earth, but is nonetheless near the Earth. So here's my system. In this case, there's nothing touching the system, so there's no contact forces, but there's still the long-range force, so I will still say there's F gravity around. My free body diagram only has gravity, so then it looks something like this. And in this case, let's actually now do Newton's second law. I'm going to define down as positive this time. Don't have to. I've defined up as positive. I'll get the same answer, of course. But let me just define down as positive this time. So again, I like to start super general. The sum of all the forces acting on the ball equals the mass of the ball times the acceleration of the ball. In this case, there's only one force acting on the object, and it's gravity, and it's pointing downward, which is the positive direction. So I'm going to write this as F gravity. I'm not going to worry too much about the vectors because this is 1D. So, this is essentially just a 1D problem. So I don't really have to bother too much with the vectors. And that is equal to the mass of the ball times the acceleration of the ball. However, we have experimental insight now that we actually know what this acceleration is. It's 9.8 meters per second squared, or what we have been using little g to represent. So we know this F gravity is m ball times g. And in this case, if you think about this for a second, we have essentially just derived what the gravitational force is for an object near the surface of the Earth. I will highlight it. So the gravitational force which from here on out for near the Earth, I will just write as a force vector with a little g, equals mg pointing towards the Earth. So if down is positive, then the force is just positive mg. If down is negative and up is positive, then the force due to gravity is negative mg. The negative, again, with vectors, the negative is telling you about direction. So by me writing down is equal to mg pointing towards the Earth, that means that the force of gravity is mg. You can think of it in the y direction if you want to. If you want, think of j as in the y direction. Maybe it's negative mgy. If j is vertical and up is positive. Again, that all just depends on your coordinate system. It has a magnitude equal to m times g, and it points in whatever direction is towards the Earth. The force due to gravity is also called your weight. In physics, when you talk about the weight of the object, what you mean is your weight. Your weight is the measure of the gravitational force acting on you. Which is why this might be slightly confusing, because you might think, well, wait, if I stand on a bathroom scale, I get my weight, and I thought that was a measure of how much stuff I'm made up of. And they're related. Notice that your mass is involved in this expression. It's m times g, but your weight in physics is actually also taking into account that you have some acceleration from gravity, in this case towards the Earth. Now, if everyone is on the Earth, then we can calibrate our bathroom scale so that all of our bathroom scales are measuring the force due to gravity, but that relates to our mass because all of us are accelerating at little g. Though if you say go to the moon, where they say your weight has reduced, you have not shed off protons in the process of going to the moon. It's just the fact that the moon is not pulling down on you as strongly as the Earth was. So if you were to step on a bathroom scale, your weight would read a smaller number because you're not being pulled down onto the scale with as much force. A bathroom scale, by the way, is just a spring. It is a big spring underneath the scale, which it is measuring. Where is my spring? When you step on a bathroom scale, it is measuring how it gets translated to a number is it's measuring how much the spring is being compressed by your weight. So even though I just said this a bunch, I will say it again. Weight is not the same thing as mass. Again, weight in physics is the measure of how much gravitational force is acting on you. Mass is how many protons, neutrons, whatnot make up your body. They are related, but they are not equivalent. Okay. Very good.